What I'll try to do is give you something that is a little bit more general, and it's a goal, if you want, that certainly is influenced by the HBP, but also other projects that I'm involved in. It has a little bit of workflow, it has a little bit of federation, it has a little bit of analytics, so we'll see what we end at the end. And I was told I'm at the Athens Research Center of the General Director there, Professor at the University of Athens, and a lucky chap in SP8 under Richard and Anastasia. So, some generalities. Big data is a big buzzword these days, and how do we get to influence medical research and practice? So in principle, what big data does is take care of your processing, take care of the provenance, Anastasia mentioned that, anonymizing your data, a whole bunch of processes. Often when people talk about big data, they mean size. Well, big data has 5 V's actually that people have talked about. And in HPP, we do have volume, well, hopefully we'll have volume, and variety, integration. We need harmonization, was already being talked about. But there's also big data we don't see very much so far in HPP, but it may come. Velocity, things coming in streams from sensors and so on and so forth. Or wrong data, is it truthful, is it high quality, the question was there. And also, okay, we have all this data, how we can extract value from it. So there is a lot of stuff about big data, just not forget about that. And then there comes the analytics, there comes the modeling of the data, take care of high dimensionality, heterogeneity that was being talked about, various analysis tools that we built, which is still computer science tools on top of the big data. And the third, in the downstream, okay, is what are the functionality, what are the tools, what are the services that we offer to our target user groups, who are the clinicians and the clinical and the medical researchers. There comes the workflow of the processes, personalized medicine, this is a big thing, and I'll mention the term a couple more times, decision support at the clinical practice, and so on. So this is what computer science can come and do. And now the dream is that will come the upstream, and the medical practice itself will change because we'll use big data in this fashion. So the ethics and privacy may need to be taken care of, and research is working on that to help us do more research. Promote model-guided personalized medicine, so you don't get all the same medicine, but based on your personal model of how your organs work and how your whole body works, come up with treatments and so on. And finally, a full ecosystem where clinicians, researchers, and patient are the whole community that interacts, provides data, does data, and is part of the process. And have a marketplace, actually, although we talk about health, there is a market around it. So this is the dream. I won't talk at all about the upstream, but knowing that this is the goal, some of these downstream computer science efforts may be effective. This is a multicolor logical architecture of rough 3 layers. Here is the kinds of data that we need to be working on. And it's, of course, lots of data that come from actual patients, current or past. But this is not the only thing. I mean, most of our efforts go here. But let's not forget, that we will have simulation models, as I said, of our bodies. Eventually, that will be personal. And also, we have a lot of top-down information that is in the heads of the researchers of the world. Okay, and these needs to be taken into account. It is data-driven, but it's also model-driven and educated clinicians-driven as well. So all this needs to be taken into account. And this, if you want, is the what. What should we be dealing with eventually? Okay, and then comes what I kind of loosely call the where all the data resides, where all the data is grabbed from, annotated, and so on and so forth. Okay, stuff like the ones that Anastasia talked about. And then you have the hub. There is where you have all the data processing engine, the data processing smarts that you will be dealing with. And then finally, the why. The why we have in order to be able to serve the clinicians, the service that we want at the upper layer. And I will not talk about the where the data is stored, where the data is grabbed from, where the data is manipulated, can be in lots of places. We will have infrastructures that are specifically being built across Europe and across the world to store biomedical data. And this cannot be ignored. A lot of things will not be in a local hospital store, will be there outside because the laws allowed it, because there is an incentive to put data in so that you can grab data from it and so on. And for example, as I was saying, Elixir is a big European data infrastructure built in the UK, and all of Europe is supporting that. There are other infrastructures, electronic for more general content, like your papers. Where will the papers? Will be in PubMed, or will there be in an open open infrastructure? And I'm just mentioning one keyword that I'm sure you'll bump onto it at some point. And then you have the special infrastructure that are built for hospitals or for special purposes, and Anastasia talked about RAW, but this is one thing that I'll mention, and others. So all this, in terms of sharing and in terms of reusing, you'll find it in a spectrum of places, each one with different access requirements. And the how, there's lots of things, how to distribute, how to do federation, how to do parallelism, how to do great things in a distributed fashion. And I'll just, in my talk, I'll talk about a system that we are working on within HPP to support whatever it needs to support. And then finally, there are a whole bunch of modeling tools I'll briefly mention and give you a feeling for some other tools that we're building again within HPP but elsewhere as well. So I won't talk about the where much. I'll just show it in a couple of times, split second. So I'm here. I'll go to the middle layer where I'll talk, which is closer to workflow. Anastasia mentioned about workflow, so she didn't lie. I will talk a little bit about things like this. So let's see. This is the EXAREME system. EXAREME with an H, actually. If I had an H, it would be a tree with 6 rows of oars. So in ancient Greece, they were doing it to very parallel rowing and very fast speeds. So that's the inspiration. So it's a system that has the distributed part and then a local part, which is MADIS that I mentioned before. I won't give you details, SQL, the version of extended SQL that EXAREME deals with, and how it works over a cloud for on-demand levels of parallelism and so on. And then locally, all the smarts with compression and other things that we're working on. And in order to put it in the Human Brain Project in the medical informatics platform, EXAREME and its local part can be placed in a whole bunch of architectures, and we'll eventually choose one of them, and you see RAW underneath the EXAREME thing, and we are intensely working lately to see, to interact. Very soon, in a week or two, this interaction will be over. And then it can be another federation layer or just EXAREME doing it. It's not important for the purposes of this discussion. Thank God we have multiple options. So what is the purpose of this system? What workflow means? Workflow means that you don't just have a query, you don't just have one thing that you run on the data and you get the result, but you have a sequence of things that can be run in parallel, can be broken and partitioned so that you have scalability. You have things that need to be run one thing after another. So you take some data, you model it, and then you grab another data set that you need to use as input in another model, and so on. So this is the overall processing that needs to be supported. And of course, it has to be done distributed over all hospitals, possibly external sources as well. and it has to deal with complex algorithms. For example, data mining is not a query. You need the more complex things that falls under hospital. One key constraint, you heard it before, it has to be privacy preserving. Okay, my shoe size cannot leave shoe, okay, because it's private, and then I don't want anyone else to know what shoe size I have. So only aggregate information is to be transferred from hospital. And of course, in order to support this complex processing, you cannot just deal with the functions that data management systems of one flavor or the other give you. You need the user to be coding something and saying, I want this to be an operator on the data next to the standard stuff. So you need user-defined functions, and you want to do all this very efficiently. So I'll just give you an animation of two kinds of such processing that is done distributedly or through a privacy wall that conceals hospitals from the outside world. So, simple example, let's say that all you want is to get a bunch of values and find how many there are and their average and standard deviation. So, at the federation layer, at the portal layer, whatever some central thing that exists, you just decompose the query into the local parts that you'll send to the hospitals and the local parts. So, for example, just get me from each hospital the sums of squares and the count. The local queries are set there. I'm abstracting here, there will be the thing that Anastasia talked about. She had it horizontally. Now it's somewhere here on the third floor, okay, running. And the local queries are, you run the local queries there. They may need some repetition of running the queries to get the correct result. Find what you need, you send the partially aggregated results, which are, for every parameter, the numbers that you wanted. You run the global query to merge all this, and here's the result. And this guy is smiling. You cannot see it, but he's smiling. Okay? Now, this part, okay, it's simple. Okay, average. Who cares about average? This is so 3 centuries ago. But now we can run in the same way many complex algorithms. And for example, if we want k-means for some k, and you want k-means to run it in a privacy-preserving way on top of anonymized data that Anastasia anonymized. So you want to decompose algorithmic steps in local and global parts, the same thing. The first layer is exactly what I said before, just the sums and the counts. And then afterwards, you start sending again local queries back to create the clusters, and you assign points to the nearest cluster. How many of you are familiar with k-means? Okay, most of you. Okay, k is hard.
What is it?
It's a means to get to a result. It's clustering. I think at some point I'll show you. Yes. So, and then you have, you go back and forth, sending always averages, always aggregated data. So, none of the results here are crossing, no individual results are crossing this wall. And then with repetition, coming and going, eventually this converges, and the centers of each cluster are stable. And the overall results are sent back again. For every parameter, you see the cluster center. So we have k clusters, and here are the centers of these clusters. Not all data mining algorithms, machine learning algorithms can be distributed in such a fashion, but many can. And we can have those, and we'll see what we'll do about that. But this is important. So let's go to the upper layer. And here is another way of workflow and thinking about how to reach from data that you have, okay, a bunch of data, which, by the way, are bottom-up data that you collect from patients. But again, let's not forget the top-down data, the simulation models and the knowledge ontologies that exist out there that experts have developed, or rules that the medical people know that when this happens, then the other thing cannot happen, or that's the right way. So we have both bottom-up and top-down information. And how do we get from this data eventually to personalized medicine? Okay. Again, this is in the abstract. It is applicable to any kind of medicine and any kind of disease. So, human brain project, the medical informatics could eventually be going through this. Okay, but also elsewhere. And this, of course, you reach here. You see what happens to patients, and then you feed back, or more data, more knowledge, and then more data mining, and cross-correlating actuals with simulated data and so on. First layer, data processing. Well, a key thing is about, one of you asked about quality of data. Okay. The data, clinical data, people's lives depend on it, but there's no guarantee that at the beginning they are clean, that they are high quality, because some instrument may not be at its best day, maybe someone copied something that was wrong, and so on. And this is, of course, very, very critical in many applications, and far and foremost in medicine. So we are developing a tool, and I'll dare to give you a quick and short demo of it now. And I have the cheat sheet that my students gave me, so hopefully I won't screw it up. So this thing is that it's a data curation and validation. If it really succeeds, we'll have to change the name, because then the Citroën will sue us for using the cerveau for an acronym. So it's interactive, it's web-based, and gives a data scientist, a data curator, someone who understands the data, but also understands the domain, understands what about human brain, or understands what about, I don't know, arthritis, or things like this, to see what rules we know the data should satisfy. So clean the data from typographical errors, or enforcing dependencies, correlations between one column and the next. Come up with medical scores. Oftentimes in medicine you collect data of different kinds, and then you don't want to use 5 numbers, but you somehow bring them together and you have one index, and based on one index you make your decisions, visualize them, and so on. So let's see if I can give you this. Okay. So there are 3 data sets. One is from HBP, the CSF protein SNP SMRI. Okay, I hope this makes sense to people. It's another one from arthritis, the juvenile idiopathic arthritis, and then this one is a fictitious toy example. So let me start from this. Okay, well, you cannot see the whole thing. Okay. Let's see. For example, a very simple one. Age onset. Age onset, when did you get the first thing? If we have the numerical filter, you see, and this is, tools like this exist, but there are very few, and they do often subsets of these things, or their interface is not very usable for non-computer scientists, for people who don't love SQL. Okay? And so what we are attempting is to give a tool that really gets you end-to-end, and it's useful to people. So you see, this is, by the way, GIA is for kids. So we do age onset, when did this first show up? And you can see the distribution, that there is one value here that is 44. Well, obviously there's a mistake. Okay? And just graphically, by just seeing this, you can immediately spot it, and then you can go ahead and correct it. I won't correct it now because it will screw other things that I want to show you. But very quickly you can spot outliers, you can spot mistakes, and then go and curate the data. And spotting the data can be done automatically. But what is the correct value? What is the correct value? Usually you cannot do it. A human has to say, okay, I have no idea, so just make it blank, or this is 4.4 or something like this. String similarity, let's go to sex. Okay, and if we see that there are 53 are males and 1 is email. Okay, so obviously this was a mistake, but then I hope I know how to do this. I can merge the selected values, and then the male now has no mistake. If you see, well, that's fine, let me not spend time on it. The value that has the highest frequency is the default value. So quickly you say, yes, email doesn't make sense, at least in this context, so press, the common value is that. And we have a problem with females as well, and we have one that was femaled, no connotation. Again, you can merge this, and then everything is clean. Okay, just examples very quickly, and from limited, I have to admit, but nevertheless experience with some other doctors in some other fields, and then in some other fields as well. Even simple things like this makes a whole difference in what people do. Let me give you, what should I give you? Okay, discretize volumes. Okay, let's go and discretize values. So this, this is on the right side. The screen is too short. Let's do something else. I see the time also. A couple more things. So let's go to the data that we have from HBP. It is whatever this says it is, and we can have. We have incorporated, and we've implemented a bunch of tools in the way I have mentioned before, a bunch of algorithms. But in this tool, we have incorporated k-means and ID3. Already, this runs on top of the parallel processing of EXAREME that I mentioned to you. So this tool runs on top of EXAREME. So let's say that we want to do k-means, okay, and this will tell me now which parameters. So frontal is 1. Frontal, and the second parameter is pallidum. Okay, and you see immediately where the points are, where the clusters are, the 4 clusters, because this was run with k-means 4. It's a parameter that I specified before. And we can go to a point and, for example, press on it, and then immediately we see the data point on the right to see the details. Again, no research, but just bringing it together and showing it in a way that you don't spend time dealing with data makes a big difference. And finally, let's go to the contact lens data set, which is a fictitious one, and let's run ID3. 1 column, which column do they want? Contact lenses. Contact lenses, I think this is it. Contact lenses, okay? And you see this, and of course, maybe in order for this to not need contact lenses to look at it, we can maximize it, then you can see the tree and so on. So, a whole bunch of other tools. I don't have time to show you, I just want to give you the flavor. And why do we spend on it? Because data quality is key, and data curation, data cleaning is a mandatory first step before you can then analyze. Because otherwise it's garbage in, garbage out. Okay? So let me go back to the presentation.
Even
yes.
for very big data sets.
even to very big data sets. There, the part where you don't, not the simple things, but where you do data mining, various knowledge discovery tools, they will show you outliers. Okay, and there you can say, this is a very interesting case. Yes, it can happen, let me do research on it. Or you can say, this makes no sense, this is a mistake, let me investigate to correct it. Okay? With huge, and as you saw, all of it was distributions. So statistics is big there, you cannot be going one by one and checking. But with statistical analysis, simple or complex, you get a view of the data and you can identify issues and problems. So it's interactive, and it's not, analysis comes further down the path as well. But even here, when you clean the data, you need to analyze it to find possible mistakes. And it's the bigger the data in terms of size, the higher the chances that it has mistakes. And therefore, you are in tremendous need of tools like this. Yes?
But I'm sorry, you do the data curation locally, right, at the hospitals, because you don't want the data to leave. I imagine if you want to, you have all the system of local queries and global, it's because you never let data leave from. So if you do curation, you don't do it from the sort of centralized point. You would do it locally.
This is orthogonal to where the data is or what the data is. So this could be installed at a hospital and be working, a person within the hospital looking at everything, or it could be hosted globally and getting whatever statistical data can be given out from hospitals, plus other data that is public, and then correlating and cross-correlating and so on. Okay. I see you, but I see you too also. So, so quickly. The other things, data mining, well, I won't tell you what we do, but it's again to find disease signature and cluster patients, find similar patients, and see, and do all this with a whole bunch of parameters, both predictors and medication are the treatments that you can give, and the outcome that you saw, both primary and also derived parameters that I mentioned that are very important. And so finding correlations among a whole bunch of parameters are the things that will give you the predictors, that will give you the biomarkers and so on and so forth. And from that, we work with Bayesian networks and other conditional probability distributions in order to find correlations between parameters. And correlations doesn't mean causation. Okay, the fact that this parameter is correlated with another parameter doesn't mean that the first one causes the second, or the second causes the first. You don't know. There are ways to approach it. It's a much harder statistical problem, but it's there. The key thing I want to, if you can look at this picture, well, let me go at this. So assume that from GI again, the juvenile idiopathic arthritis, we have a whole bunch of parameters. Okay, and we have arcs, mean correlation. This parameter is correlated with this 4, has nothing to do with this one, for example. And now interactively, this is another tool that we have, I will not demo that. Having this, you can play, and okay, you have, for every parameter in general, from all your patients, where things are. But now you can ask, what if? Well, I have a patient that I know that his RVD, whatever that means, is moderate. Okay, so let me make this, fix this. And 25% of my patients actually have that. How are the other conditional parameters, conditional probabilities are affected? So for these cases, not in general, where this is, all of them are 0%, you see most parameters go down. Immediately you can see interactively correlation, it's not a static thing. And again, from limited experience with some medical doctors, okay, this interactivity gives them insights into the data in order to reach a decision based on that. And then you can see how sensitive its parameter is. So again, a whole bunch of things in tools like this are important. So, parting thoughts. Big data is not only about size. Size matters, but it's not the only thing. Data is distributed, data is heterogeneous, so we have to take care of this, and the process, the privacy makes the whole thing even more challenging. So we still have work to do tomorrow. And processing goes to data, not data to processing, not only because of privacy, because it makes sense, because it's more efficient, because it's cheaper in whatever way you want. And the advances, there are a whole bunch of things that people are working on, including my team, on compression, federated processing, scalable, data curation, text and data analytics. I didn't talk about text, there's a lot of text, but hey, I cannot talk about everything. So, these are a bunch of human brain projects. Of course, another medical project. Thank you.